If you spend any time in the American Midwest during the winter, chances are you've seen something like this before. Solar panels, partially or entirely covered in a blanket of white snow. With heavy snowfall, they can even begin to look like this. Many residents of snowy areas tend to mostly care about this powdery disruption of infrastructure when it sticks to the road. But for solar panels, any amount of cover from being completely buried to even a light dusting can cause a significant drop in power production. To optimally utilize solar panels in these environments clearly requires some cleaning method, and the market agrees. Many solutions have sprung up to tackle this problem, including a number of autonomous ones, but they lack an incredibly beneficial piece of the puzzle: scalable data collection. Many solar fields rely on a small number of cameras to gather broad information about the state of the facility. At smaller facilities, if the camera shows snowy panels, then the cleaners are called or robots dispatched to deal with it. The problem comes with larger facilities. You either have few cameras, all with limited viewing capabilities, or many cameras, which, while fairly cheap in the modern day, will still become quite expensive with scale. Instead, we can use a drone, giving us the ability to cover a large area with a single moving camera, collecting all of the data that would be provided by the vast network, but without the immense cost. Now the question is, how do we use the captured images and video? We certainly don't want to have a person manually reviewing the material. That could take a long time, and any sort of consistent result would be all but impossible. Our solution is to utilize a machine learning algorithm to pick out the solar panels from the image. Then we can analyze those parts of the image to collect information. We developed a program to do all of this, which follows this flowchart. Keep in mind that this is not an exhaustive explanation of the program, but rather a brief overview. On startup, the program prepares for the image processing by loading the machine learning algorithm, GUI, and database. Now the drone images can be processed. For the sake of higher quality images and saving on resources during processing, our currently used data collection method involves a drone taking a snapshot every 5 seconds. The frame processing loop iterates through each one of these snapshots until there are no more to process. First, the GPS location is extracted from the metadata, then it is compared to our set of regions to determine at which location the image was taken. The frame is then segmented by the model, returning a set of masks which can be messy and include overlapping masks. This set is cleaned up a bit by culling the redundant masks before it's handed to the mask loop. For every remaining mask in the set, snow coverage is calculated by analyzing the radiance of the image in an area indicated by the mask. Bounding boxes are also generated at this time, before the frame is annotated with the boxes, snow coverage percentage, and region. When the mask loop is fully finished, the average snow coverage across the frame is calculated and, in tandem with the region information, is used to update the database. Shortly thereafter, the GUI is also updated to reflect the database changes. All in, this program processes imagery from a number of locations and reports the average snow cover at each of those locations in real time. The work that would take a person a period of hours to accomplish is instead done in seconds. This is the current version of the GUI. It updates with every frame, displaying the annotated image and running mean for that region. The text is color-coded as an additional signifier. The frames that you're seeing now are actually used in the training of the model, so this output is quite accurate and clean. These frames, on the other hand, were not used in training, and were actually intentionally taken in different lighting conditions. This is a difficult dataset for the current model to process, but further training and refinement is planned so consistent results can be achieved across a wide range of scenarios, angles, and atmospheric conditions. I'd like to end by expressing gratitude to Dr. Anna Dyerson and our advisor, Dr. Ashraf Saleem, for providing guidance over the course of the project, and to Zoe Mazurkiewicz, who gave us valuable input early on in our design process.